Good morning, everyone. I believe that you can all hear me. Okay. Right, so today we want to look at the last part of our chapter 16, and it's actually the concluding part of that chapter. At the beginning, we saw that we'll be discussing 3 major blocks, and we established at the beginning that we'll be using what we called wave model to understand different concepts or principles about different kind of waves. And we're able to differentiate the wave model from the particle model that we saw in our term 1, first term, and how that they are different. And what we mean by wave model is that we'll be looking at fundamental principles of wave and how that these principles apply across board or apply to all kinds of waves. So when we say speech and hearing, we're just going to be looking at certain principles as well as applying from sound wave, and that applies to every other type of wave as well. Okay, so most of the principles we're looking at it, yes, with the example of sound wave, but in terms of wave model, meaning it applies also the same way to other type of waves. So today we'll be focusing on speech and hearing. And we'll be looking at some other subtopic under that. Last class we've been discussing wave, and we've been discussing different type of transverse and electromagnetic waves and different concepts or model to describing the phenomena of wave and how they are formed. So when you hear a note that is played on a guitar, for example, if you play a key on a guitar and you play the same note, the same key on a different instrument, say trumpet, you are able to say, oh, this is the key from this particular note, this particular instrument, if you are used to that, and you're able to say, oh, it's different from the one played on a different instrument that you're not used to. Even if the keys played were the same or notes played were the same, the sound that comes to your hearing is different. And the same thing applies to when you speak. If you want to use the vowel sound, different vowel sound, or and so on, you notice that the sound of what comes out from your mouth, the pitch, they are different, and you're able also to tell the difference. So we'll be looking at the details of how you're able to tell the difference between the key played on different instruments, even if they are the same, and how you can distinguish between the vowel sounds and how these sounds that you make comes to you and your brain is able to interpret it and say they are different. Well, that is basically the summary of what we'll be looking at under speech and hearing. So let's look at the figure before us here. We see the frequency spectrum and a graph of the sound wave on a guitar played. We play the guitar on a note at fundamental frequency of 262 Hz. Okay. So the figure A is showing us the frequency spectrum, and the figure B is the one showing the graph of the sound wave. We'll be looking at it after this slide. Now, we see the graph of this graph showing the frequency spectrum of a key played on a guitar. We play notes on a guitar and we make the plot of the frequency spectrum. This is what we have. The plot of relative intensity against the frequency of the note played. Now, the very first bar here with the highest peak is what we refer to as the fundamental frequency. Okay, and then we have, apart from the fundamental frequency, other frequencies, because when you make a sound, it's actually a mixture of several sounds, but it is a particular sound that distinctly comes to you, and it is that sound that we call the distinct sound that comes to your hearing is from the fundamental frequency. You remember what fundamental frequency is when we discussed in the last class about standing wave, and we're able to point out the fundamental and the higher harmonics. So I don't have to explain higher harmonics again. They're simply harmonics above the very first one, which is the fundamental. So if we have the range of our harmonics here in the fundamental, so this is the peak showing the fundamental, and the fundamental is 262 Hz. We see other higher frequencies and their peaks as well. So these bars is a description of the spectrum for a different frequency in that mixture of sound that was produced. Okay, and that is what we call the spectrum of the note played. The several bars represent the spectrum of those notes. Okay. So when you hear a sound, it appears to you as a distinct sound, but it's actually a mixture of the spectrum of frequency, although it is the fundamental one that distinctly comes to your hearing. Okay, so let's see the second graph, which is the graph of the sound wave of the guitar that is playing the instrument at this frequency. So we see the graph, the wave graph of the same notes played on the guitar. If you notice the wave graph, you can see that this wave is periodic. You can see it's having the same pattern. So from this point to this point is the wave period. So the wave period for this note produced at this frequency of 262 Hz has the period of 3.82 milliseconds. Okay, so for the period, the plot of the atmospheric pressure, the change in atmospheric pressure was plotted on the vertical axis, while we have time on the horizontal axis to give us the sinusoidal graph that we see here, although it might not be as smooth as what we used to represent as sinusoidal, but it's typically a sinusoidal description. We've explained why it has to be a smooth description in our very first, when we discussed chapter 15. All right, so the higher harmonics, as we saw in the first graph, did not actually change the period, but what the higher harmonics do to the sound you hear is that it can change. They only change the shape of this graph representation, the sinusoidal graph representation, but not the period itself. The period will remain the same because you are playing the same note. So if you have the same note played on a trumpet, it's going to sound differently from what you played on a guitar. It is actually the higher harmonics that brings about that change, that difference in sound, but the period remains the same because it's the same key that you're playing, it's the same notes. So let's say you make a sound on a trumpet at the middle C, the same way you did on your guitar. They have the same period, but what makes the sound to be different is that the shape of this wave graph becomes different from that which is produced from the guitar. And the difference in this shape is actually the difference in the spectrum, different spectrum size, that's this bar sizes, height, for the higher harmonics. So the frequency is the same, the fundamental will be the same, the shape will be different, and it's that difference that brings about the entire difference in the sound that you hear, and you're able to say, oh, this is sound from a guitar, this is not. Okay, so have it in mind or understand the point that it is actually the higher harmonics that brings about the different shape in the sound wave graph, and that is what actually inform the difference in the sound you hear from two different musical instruments that play the same key at the same frequency and period. Okay, so well, we have seen a typical graph or spectrum representation of the frequency that can be played on the instrument. Now, what actually happens is that on the note, we have established that it's the higher harmonics that brings about the difference that you hear. But what actually happened to us as humans when we hear the different sound is that our brain have a way of interpreting the mixed frequency from the guitar, as we have seen in the figure above. When a sound is produced on a guitar, it comes with mixed frequency, but one distinctly stand out, which is the sound that comes to you. And that one is what we call the fundamental frequency that was played at this frequency value. And that sound that comes to us audibly is what we call the pitch. And that is what corresponds to the notes that was played at the middle of that musical instrument. So your brain or our brain uses the higher harmonies to determine the tone quality. And the tone quality is what we call the timbre. So when you hear a sound, instead of our brain to hear the mixture of the sound, it's going to pick the distinct sound from the fundamental frequency, which we call peak, to give us or tell the quality of that tone that was played. So we're able to say, oh, this is what is played on the guitar. No, this is not from the guitar, even if you are playing the same notes on the two instruments. So the tone quality and the higher harmonies is actually, if you are asked a question, why do we hear, or you should explain why when you play the same key on different instruments, we hear different sound. You should explain why. You should be able to point to this fact that one, the sound is produced by mixture of frequencies, and the one that comes to you or comes to our hearing is the fundamental frequency, which is called the pitch. And with the pitch and the higher harmonics, we're able to determine or define the tone quality, which is called timbre, and with the tone quality and higher harmonies played on that instrument, the difference of the sound is made known from the difference in the sound, in the wave shape, okay? Because the higher harmonics in the spectrum will be different from the guitar and the trumpet, so the shape will be different. And the frequency spectrum of the trumpet will be different from that of the guitar. So you will hear a relatively different sound, or different because of the difference in the pattern of the wave diagram. So you should be able to put those points together to explain the difference distinctly. Okay. So proceed to vowels and formats. Vowels and formats. Now, at the beginning of this lecture, we mentioned that outside differentiating notes from word to hear, when we want to make different sound as we speak as well, We speak at different pitch, but we're able to hear distinctly what we say and understand each other. But how does that happen? How are we able to say, oh, this person is speaking at a high tone or a low tone, high pitch or low pitch? So we want to look at vowels and formats. Now, what we mean by formats is typically the broad standing wave resonances of the vocal tract called the format. So when you speak, the vocal tract acts like a connection of tubes, because on your vocal tract, when you speak, you're actually using all the openings from the nose, ear, and all work together to give you the particular pitch or sound. That is why when you're talking and you close your nose or your ears, the kind of sound that you produce tend to change, even if you're speaking at the same pitch. Okay, if you're speaking at the same frequency or a mixture of frequency, the same pitch, let me use that word, you kind of hear a different sound when you close your nose, close your ears to talk. Okay, so what we call format is actually the broad standing wave resonance from your vocal tract. Okay, so whenever we use the word format, that is what we mean. You know what the standing wave resonance is, the resonance vibration of the trough and crest as the amplitudes. Okay, so the vowel is the same thing like the vowel sounds, you know, so that did not change. So let's look at, to understand these two explanation of how we hear sound and make sound. The figure A before us, the frequency spectrum, you know, frequency spectrum showing you the bar of relative intensity against frequency. Okay, so this is typical frequency spectrum of, this one is a typical frequency spectrum of our vocal cords after, and this one, the B, talks about after passing through, sound is passed through the vocal tract. So this is the frequencies from the vocal tract. This is how the different frequencies that can come from the vocal tract are represented, from 0 to 3000 Hz. So when you speak, your vocal cord produce a mixture of frequencies, just like when you play a note, mixture of frequencies are produced, but one is going to be distinct. That is the one called the fundamental frequency. Okay, that's sound. Now, importing that idea that we saw into the explanation of how we make sound and hear sound, we look at the B part, which is the actual spoken frequency when you make the voice sound A. So when you form your vocal tract to make the voice sound, this particular voice sound, it increases the amplitude of certain frequencies and suppresses some. So the increase and suppression of these frequencies makes the fundamental frequency to stand out. And that fundamental frequency is what we are referring to as the format. Those sounds that are standing out, they are the formats. So we'll have the first format to be the fundamental frequency, and the other, this is the first format, which you typically call the fundamental frequency for sound description, but for vocal or when you speak, we call it first format. Okay. And I've explained that format is simply the broad or a combination. Let's use that word, the broad standing wave resonance. That is the resonance vibration of the amplitude of the standing wave. So this is the first one, which is the broad peak at which the amplification occurs due to the filtering of the format. So what happens is that when you make a sound, you talk, some frequencies are suppressed. The frequency around this particular first format, they are suppressed. Before you hear another sound that stands out again, which is second frequency, so this stands distinctly out to the hearing. So in order to clearly hear this what is called the higher harmonics, if we use that sound, but in this case, we're not using the higher harmonics, we're using the formats to describe it. So the frequency around this format has to be suppressed for this first format to stand out. So these are suppressed so that this can stand out to our hearing. And then we'll have other formats coming up, which can be accompanying sound to when we speak. Okay, so the difference in sound arises from the difference in the higher harmonics, just like we have seen in terms of in the description of the musical instrument. The difference when you make sound is also coming from the different shape, that the different spectrum that the higher harmonics will form, which will give rise to different shape of the sound wave graph. The sinusoidal graph, the shape will be different. So that is what brings about the different sound that we hear. And we have already established that how the sounds are produced is by suppressing the frequencies around the fundamental, which is the first format. Okay, so as you speak, you adjust the property of your vocal tract to produce different mix of harmonies to make the sound, such as o, a, and so on, and other voice sounds. So that is why when you go for vocal checkup or treatment, they ask you to make certain sound so that they'll be able to see through the vocal cord and also see how it connects to other connecting pipes or openings such as your ears, your nose, and so on. So to really produce sound, what we actually do is to begin with the vibration of our vocal cord. We produce sound by allowing that from the vibration of our vocal cord, we stretch the tissue around our throat so that the vibration is similar to the wave on the string. That is, the vibration is of what we want to say will come out, and the description of that can actually be the stretch on the string can actually be used to describe the kind of wave that is produced from the vibration from your vocal cord. So that is why we can use or apply the same principles as that which applies on the string of a guitar to describing the vocal cord wave as well. So typically when you make a diagram, a wave diagram, it's still going to have the sinusoidal shape, but different according to the sound that was produced. So in ordinary speech, the average fundamental frequency for an adult male will have 16 research value for it, and the female is 150 for male, 250 hertz for female respectively. That is why you see that it's like the female kind of speak with high pitch, while the male have deep or low pitch tone. So whenever we want to change the sound, we can actually do this by changing the vibration frequency, and that is done by changing the tension on your vocal cord to producing sound. So you actually modulate the sound you produce or control or change the sound you produce by adjusting the tension on your vocal cord. So the harmonics of your vocal cord are near the fundamental frequency, which is the first format. We have established there in the first diagram. This is just notes to explain what happened in that diagram on the figure above. That those harmonics around or near the first format are actually suppressed so that we can hear the sound of the first format, which is the fundamental frequency, distinctly to say that this sound is coming from the letter E or U or A and so on. Okay, so that typically, the figure we saw is typical example of an adult male adult making the sound E. So, like we have stressed, that you can change these frequencies to make changes in the way this sound will come out. Especially when you want to speak, you notice that you make changes to the shape of your mouth, the opening, the position, the shape, and the tongue all work together to produce the sound you want to produce. That's what we mean by that the vocal cord works like a connecting, is a kind of connected pipe system, because before you make a sound, a lot of things has to be put in place, like the shape of your mouth, the position of your tongue, the vibration from your vocal cord, and so on. So that is how we produce sound, and that's how also we can differentiate or modulate our sounds. We have this as research rough values for when a woman is making the sound and the man is making the sound. These are the rough frequencies for the first two formats, which you have seen. We saw the first format as the fundamental frequency, the second format as the next format that stands out after the suppressed formats around the fundamental formats. Okay, so let's take this class activity to drive home that point before we move to the next sub-discussion. So if you speak at a certain pitch, then hold your nose and continue speaking at the same pitch, your voice sounds different. Why is this? Which of these options answers the question? A, the fundamental frequency of your vocal cord has changed. B, the frequency of the harmonics of your vocal cord has changed. C, the pattern of the resonance frequency of your vocal track has changed, thus changing the format. Which one is the answer? Like I said, this question is just typically asking you, why is there change even when you are using the same, speaking at the same pitch, but you just made alteration to one of the connecting pipes to your vocal track. Okay, so the answer is C, because C captured everything about how this is different when you hear the sound, and it's simply the summary of what we mean by the higher harmonics controlling or helping us to differentiate the sound you hear when the frequencies are modified. Okay. So this particular assignment, I have been writing assignments in every of our lectures, and also give assignment from the test, the problem set. So you are expected to answer the assignment in the slide, because in addition to the one from the problem set. So let's say we'll have two assignments now here, assignment number 1, 2, and then I'll post assignment saying maybe you should solve problem A, B, C, or the problem set. That means you're solving a total of 5 problems. So please endeavor to add the assignment of the slide to the one that will be given from your test as well. Okay, so this will form a part of our assignment 3, and I expect you to show your working, not just for this one. We have the option, and I'm expecting you to show your solution on the particular option you choose. Okay, so we'll proceed to the next, which is a continuation of how we hear and make sounds, speech and hearing, remember. So we're talking about interference of wave from 2 sources. We looked at interference before, so we are not meeting the term the first time. We saw interference the first time when we discussed superposition of waves, right? We saw the constructive and destructive interference. We'll be seeing that again as we explain how we hear sound from two different sources. So we want to look at the interference of wave from two sources and how you can hear them. Let's look at the diagram, the figure A before us, which is typically what we want to look at. The two sound wave overlapping along a line. See the speaker 1, speaker 2, they're producing sound. And remember we said the principle of superposition, that wave can travel through each other, okay? They can superimpose, forming destructive or constructive superimposition, which is interference. Superposition of waves is called interference. So if these two waves travel together and they superimpose, what is the sound you hear at this point? That's the question we want to address. Then we have it also, the arrangement of the two sound overlapping in terms of the spherical sound. What sound will you hear here? So we see this one is along the line, but this one is coming off a spherical interference. We have seen before the spherical, circular, and plane, right? Recall that we need that to understand the discourse here. So what sound is going to be heard at these different dots? So I want to explain that using the interference phenomenon. Okay, so looking at the very first scenario for A, which is the interference along a straight line or along a line. Now, we have two sources of sound. We have two sources, and then the speaker 2 produces sound and the speaker 1 is producing a sound. We use the orange and red to differentiate the colors. We see from the diagram of the wave graph that the speakers have one wavelength and the distance apart. So because it's a complete one wavelength, we see how that the wave from the speaker 2 is perfectly superimposed on the wave of the speaker 1. From this, we can tell that they are moving at the same wavelength, frequency, and amplitude. Okay, so we see the crest coming into the crest of the second one, the trough going into the trough of the first one, and at the point, both come to this point where you can hear the sound. All right, so we see the distance for the first one, the second speaker, speaker 2, and the distance for the first speaker. The difference in these two distances is what we call the path length difference. Okay, so the path length difference is represented by change in D, while the D, which is distance difference, the graph here is the total or the superimposed sinusoidal wave. That's the wave shape you have here. When these two combined, that's what we have here. So the blue line, if we say the blue line is a representation of the combined wave, because they superimposed and they traveled together to form constructive interference. So the trough coming to the trough, the crest coming to the crest, formed something that gave the amplitude, that made the amplitude larger than the individual amplitude. So the superposition of the two waves made the amplitude larger than the individual amplitude of this wave. It's a sum. Remember the principle of superposition that we talked about, the sum of the two. So if the sum can either give us a 0, which is nullified or canceling out the wave, or make it amplified, make it bigger, larger, so the amplitude becomes bigger. So the superposition is a traveling wave with the wavelength and twice the amplitude of the individual wave because they are sum, a combination. When this happens, we have what we call the constructive interference. So typically, we have a constructive interference, and that is why you can hear the sound at the point or dot or that to be a sound with a larger amplitude. So the wave align in a way that we can say this alignment pattern, we use the word that they are in phase to describe it. So the wave are in phase, that means they match step by step to each other and they can combine perfectly to form a stronger wave. So let's see the second combination here. No, before we see that, that is what can happen when it's constructive. Now, what can happen when it is destructive? If the distance between these two sources is such that they are actually half wavelength apart, what will happen? It will give us, let's look at the red, look at the green, that's the speaker one, the speaker two. You see that we have something, the shape that looks like the description of what we have as standing wave, but this is not a standing wave diagram, okay? This is the wave diagram telling us that the trough of wave from sound one is tallying with the crest of sound two. And when that happens, they cannot combine perfectly, right? We say that they are out of phase. This description is, we use the word that they are out of phase, they're not in phase. So when they are not out of phase, we are going to have something we call destructive interference. The sum of these two will lead to cancellation or zero at that point, which is termed destructive interference. So the same apply, the D being the path length difference, and the superposition of the two waves will give us a zero amplitude because they will cancel out to give us a straight line. So at this point, you tend to hear nothing. Why? At this point, in the first case, you hear a loud sound, distinct loud sound. But here, it's a point where you don't hear the sound at all because the amplitude becomes zero. The superposition cancelled out. So from our knowledge of principle of superposition, we can see that the summation of the two identical wave sources gave us the constructive interference in the scenario. And then we have that the path length difference is given by this equation, change in D being equal to M lambda, and M is the range of integer. Remember what your M is, your mode number. And for the destructive interference, that is a case where the distance between them is a fraction of the wavelength. We have the path length difference to giving us change in D equal to M plus half lambda, when M is a typical integer as well. So let's see an example to see how we can apply that to solving problems. All right. We'll see this example, then we'll look at what happens with the spherical interference or superimposition as well, just as we've seen for the first one. So Susan stands directly in front of two speakers that are in line with each other. The further speaker is 6 meters from her, and the closer speaker is 5 meters away. The speaker are connected to the same source of sound of frequency 880 Hz, and Susan hearing the sound loud and clear. The frequency of the source is slowly increased until at some point, Susan can no longer hear it. What is the frequency when the cancellation occurs? Assume that the speed of the sound in air is 340 meter per second. So first we look for the change in D. The difference is 1 meter. And the initial from the relationship V equal to lambda F. We look for our initial wavelength to know how these two are really set apart. What is it by integer wavelength value or fractional wavelength value? So we see that, we see the wavelength is 0.5. Okay. So that will give us an idea of what because the question is, what happens when there was a cancellation? The fraction tells you that the wavelength is actually the destructive one. So we see a kind of pictorial virtual representation of what happens. We see the crest tallying with the trough, so there'll be a cancellation. But the question is, at what frequency did this happen? And we're looking for F. So we'll proceed to solving that when if the wavelength is a whole number, the initial wavelength is already this. From the relationship of when it's constructive and when it's destructive interference, we see the module 2, M is 2, and then look for the change in the path length difference. We apply that. We already know that this is 2, which is your M. We now give you half lambda, which is half is the same thing as 0.5. So that's our half 2.5 here. So the final, this will be your final wavelength. This is the initial wavelength. So from this, we can actually get our final wavelength. Change in D is equal to 2.5 final wavelength. If we make the final wavelength the subject of formula, since we know the value for change in D, we put that. We have looked for change in D before. Change in the distance between the two is 1. One is 6, one is 5. The difference is 1 meter. So we'll have our final wavelength to be 0.40 meters. So the corresponding frequency from this relationship as well will now give us F frequency equal to V over lambda, which is the final wavelength and the velocity of the sound in air. The final frequency, therefore, is 850 Hz, which is far higher than the initial frequency. Okay, so it was increased to the point where they achieved the fractional wavelength difference, and then it canceled out. Susan can no longer hear that sound. All right, so we'll take the second scenario for those two speakers that are arranged in this form to give us the spherical shape, and therefore we'll be looking at the spherical interference. So it is actually this principle of destructive interference that is applied to the headset that you buy, that you say, oh, does it filter out noise? What actually happens is that the headsets have a kind of speaker outside that takes the background noise, sends the signal somewhere into the circuit of the headset, and the circuit of the headset produces a counter wave signal that nullifies the external sound. So that is how the headset is able to control or reduce the noise that comes into what you hear. Okay, it filters out. That's exactly how the headset filters out the background noise by collecting the background sound, produce a signal, and internally produce a counter signal that typically form continuously the destructive interference with the background sound. Okay, so if you're asked to explain that principle as well, you should be able to use your understanding of destructive interference to explain that. Okay, so if the two speaker is set up like this, remember we said in the first case, we'll have something like the spherical wave. And that is what we want to look at. What sound will you hear at that point? Remember the first diagram. What sound will you hear at this point? So the sound from speaker we have seen in, is it the first class or the second one? I can't remember if it's on Monday or Wednesday, but we've seen previously that sound from the speaker is actually a typical example of spherical wave, and the spherical wave is like this circular wave as well. We see a source, then we see the stick line being the crest, and the space here the trough and the crest. So the distance between two crests is the wavelength. This is the source, and we have the distance, total length from source to the distance or a point of description. Then we have the wave speed and the direction in all direction. Okay. So this is a source. So when you have two sources like the two speaker you have there, they both generate the spherical wave, and you know that wave travels through each other. So this is a typical one showing how that these two spherical wave generator will travel through each other. Now what happens, the speaker 2 produces a sound that produces 1 crest, 2, 3, and then we'll have 2 strophe. The second one also produces 1, 2, 3 as well, and they traveled amongst or through each other. Now at this point, you see this is the trough, right? The middle point here is the trough. So you see the crest superimposed on the trough, and we'll have the destructive interference at that point. But when the crest of the speaker 2 superimposed on the crest of the speaker 1, we have the constructive interference. So in this spherical shape, we have the combination of constructive and destructive interference going on at this kind of setting. So the two sources emit identical spherical wave, and we'll have the R, the wavelength, which is the distance between the two crest or trough, and then R, which is the distance from the source to the particular place you want to describe. Okay, R2 representing the distance from speaker 2, R1 the distance from speaker 1. And the formation gave us constructive and destructive interference. Okay, so we see that for spherical wave, in the other case, we're using the path length description was changed in D. Here we're using path length description to be changed in R. It's the same thing, talking about difference. Okay, so for constructive interference, it's the same m lambda when lambda is an integer m, and then for destructive, lambda is fraction of lambda, which is half lambda. All right, so it's the same thing as what we have seen. And typically what you should keep in mind is what we have captured in this tactics 16.1. The difference, to identify the path difference from each source, we compute the path difference and we take what? The magnitude. Magnitude, that's telling you that the signs will not matter. We're actually going to be focusing on the value. Okay, so we also find the wavelengths when they are not specified. We use the idea of the integer wave lambda to get the constructive interference, the fraction, which is 1.5, 2.5. There's always a half lambda to describing the destructive interference. So these are things you should keep in mind about destructive and constructive interference. So let's see an example here. Two speakers are 3 meters apart and play identical tone of frequency 170 Hz. Sam stands directly in front of one speaker at a distance of 4 meters. Is this a loud spot or a quiet spot? It's simply asking, will Sam hear a sound? Would this be a constructive or a destructive interference spot? When it's constructive, Sam will hear a sound, loud sound. When it's destructive, Sam will hear nothing. It's a quiet spot. So we also want to assume the value for sound in air to be 340 meters per second, the speed of sound in air. So to visualize what actually happened, Sam is standing here in front of one of the speakers. The speakers are 3 meters apart. So the distance R1 for Sam and the distance R2. So to get the difference in this distance, our distance for Sam is given to be 4 meters. So we use the Pythagorean theorem to get this. So using the Pythagorean theorem to get the R2, we calculated R2 to be 5 meters. So we look for the path difference, path length difference for R1 and R2, and we found that it is actually 1 meter. So if you compute that, because you have to find the wavelength to have an idea if it's going to be constructive or destructive interference. So you have the speed of air is given, the frequency is given in the question, and we'll have the wavelength to be 2 meters. Okay. So we see that the wavelength is 2 meters, but the path difference is actually half what? The wavelength. So the path difference between the two is what? Is half the wavelength. Therefore, the path difference being half the wavelength tells us that this will be destructive interference. Sam is standing on the quiet spot. So the wavelength information and the path length information gave us the answer the question we're looking at. The path length, is half the wavelength. Therefore, Sam is standing at the quiet spot. There's a destructive interference. All right, so we'll move on to the last part, which is beats. Beats. How is this different from the first to discuss? The pitch, sound, and the interference. They are typically the same description for sound, but with slight difference. Okay, so when we say beat, we are talking about a distinct sound pattern that we hear when we make sound. Could be majorly from musical notes or from whatever we can use to produce sound. But what we actually want to focus on here is that from beats, we notice that we have a periodic variation. For us to say something is a beat, it will have a periodic variation, and the wave reaches our ear such that we can hear distinct sounds that are modulated in a defined pattern. Okay, so it is this distinct sound in a defined pattern that we call beats. So it comes to us with the up and down volume or soft, loud and soft, distinct motion. But actually, they are single tone whose intensity are modulated. So that is what we call beats. So let's look at a typical sound wave of a beat. We have two sound wave of slightly different frequency that comes to your ear. You're producing two sound wave and it's coming to your ear like a beat. It's coming to your ear because you are referring to it as beat because it has a periodic variation and it's modulated and it has a distinct sound pattern. So you can refer to it as beats. Okay, so we have one, the orange and the red here. If you see the way the sound wave is coming off, you notice something at this point. They are constructive, destructive, and constructive, right? It simply tells you that these two sound waves have slight difference in frequency, and that is why they are their superimposition is coming off, like the constructive, destructive, and constructive. Just a typical of what you see in a spherical interference, like we saw earlier. You see the constructive and destructive playing out in the same traveling, when the wave are traveling through each other. Okay, so this is the combination, the superposition of the two waves. You see how that this region is constructive, this is destructive, it cancelled out, and it goes to constructive as well. Okay, so if you have something whose wave formation is like this, that's where you have this sound, you hear it again, another sound, and that after a short interval, you hear it again. You have a periodic variation of the amplitude coming to your hearing. Okay, so the complete mathematical analysis of what actually happened there is that you have the frequency of these two wave coming to your eardrum. The oscillation of what you hear eventually is actually the average of these two. Okay, so the frequency of the air that oscillates that you hear after producing these two sounds is the average of the frequency of the first and the second. Now we said something about beats, that the intensity, they come to you as single tone because their intensity is modulated. So let's look at that phenomenon of modulation. Then we're calling it today. So we have seen the oscillation frequency here, which is the average sum of the two. But when it is in terms of beats, we will be describing it with what we call the beat frequency. So the intensity of the sound is modulated at a frequency called the beat frequency. And how is that done? Let's look at this figure here. We see the medium of the oscillation frequency here inside. See it, the different frequency. But the thick one here that forms something like the standing wave is the amplitude. You see, this is the one inside is the oscillation frequency, then the amplitude is slowly modulated to give you the frequency, beat frequency here. So when it's modulated, we can get a distinct single tone that comes to you. So we'll have the loud places of amplitude, the soft where you experience a quiet, then the loud again, the soft, the loud. So you have this and this combined to give you one beat. Beats, okay, one beat. So that which you call like the wave length or period is what we call the one beat in terms of beat description. Okay, so that is one beat, crest to crest, one beat. So this is a typical modulation using the change in atmospheric pressure against time to control the sound you hear. Okay, so let's look at this in class activity. Then we'll be done. So you hear 3 beats per second when 2 sound tones are generated. The frequency of one tone is known to be 610. The other frequency of the tone will be what? Or what will be the other frequency? We have option A, B, C, D, E, F. Okay, so the answer is option F. Why? They give us the frequency of one. They're asking us to look for the frequency of the other, and also they gave us the frequency in the sense that it is actually 3 bits per second. So if the frequency of 1 is 16, it's going to be plus or minus. Okay, so if it is plus, we'll have +3, where we're having the answer, we choose the answer B or C. So B or C. +3 to 310 will be 13 Hz, and minus will be, so the second frequency will either be B or C, because this is the frequency, individual frequency, and adding it to this will give you C. Subtracting from this will give you B. So the answer is either B or C. So we'll have other practice problem for you to play with. And expect to see the assignment for chapter 16. And I'm saying that you should solve the assignment in this slide, in addition to the one that will be posted on Moodle later. All right. If you have any question, explanation, request, let me know, and we'll have every concern resolved accordingly. Thank you so much. Have a great weekend.